Okay, so we are now ready to introduce a new concept, that of the equipotential or equal potential. So the best way to start thinking about this is actually by analogy with a topographic map. So any of you who are hikers know what a topographic map is. If you are thinking about hiking on this mountain, you are given a map and you plan your hike. On that map, there are contours, and those contours represent the same information as this three-dimensional perspective view. Here's the top of the mountain, here's the bottom, and these contours are lines of equal height. So if I go and look at the topographic map, I see contours C. Each contour C shows the place on the map where the height has a certain value. Exactly the same for us, except instead of height, we'll be talking about potential. So for us, we'll have a potential landscape with a peak here, and the contour C is a line on the map where the potential has the same value. So how does a hiker use a topographic map? Well, the first thing she does is she looks on the topo map to see how tall the mountain is. But then the next thing she does to plan her route is to ask, where is the steep path? Where is the less steep path? Maybe she wants to challenge herself and find the steepest path, get up there quickly. Maybe she's concerned about not taking a path that's too steep and she might choose to pick a less steep path. But either way, what you principally use a topo map for is to find paths that are either steep or not steep. What does this mean for us? Well, steep for us, the slope of a potential landscape, that's the electric field. So steep for us means large electric field. Less steep for us means small electric field. So when we look at a topo map, or when we look at an equipotential map, we look and see whether the lines are close together. If the lines are very close to each other, that means that the slope of the landscape here is steep. As I go from here to here, the potential is changing by a lot. So steep potential landscape means a large field. So right here, the field is large. Over here, on the other hand, the lines are much farther apart. Much less steep landscape here, much less steep potential landscape here, much smaller electric field. So what we are going to do in the next few minutes is get used to this intuition, and so that we can realize that we can represent the same information either by showing the electric field or by showing a nice perspective map of the potential landscape or by showing the equipotentials. We're going to be doing all of this in 2 dimensions. Our equipotentials will look like this. There'll be contours in 2 dimensions. We could do this in 3 dimensions. In 3 dimensions, we might have some configuration of charges, some close, some far out like that, some close to me like this, some over here. We could map out the potential landscape in 3 dimensions and then draw equipotential surfaces instead of lines. An equipotential surface would be a surface along which the potential is everywhere the same, just as here an equipotential line is a contour line along which the potential is everywhere the same. We will actually, all of our examples will be 2-dimensional, but this could all be done in 3 dimensions too. So somebody gives you a set of equipotential curves. What do you learn from this? Well, on each one of these curves, the potential is the same. So on curve C1, the potential V has one value. Curve C2, the potential V has a different value. On curve C3, the potential V has a third value. If that's all you know, you don't know whether this is a potential hill or a potential valley. You have to know, but if somebody furthermore tells you that actually the potential here is larger than the potential on this curve, larger than here, then you've got a potential mountain. If the potential is smaller here, then you have a potential valley. Potential mountains associated with some configuration, some clump of positive charge, potential valley associated with some clump of negative charge. So from the equipotentials, we look and see where they're close together. That will tell us whether the electric fields are large or small. And if you go back here and remember that electric field is the gradient of the potential, what does that mean? The electric field points in the downward direction. It points in the direction perpendicular to the equipotential. So if I have an equipotential here, the electric field is pointing in the direction down the slope. So if I go over here and ask what direction does the electric field point, well, everywhere on this map, the electric field is pointing perpendicular to the equipotential lines. And here where the lines are close together, the electric field is large. Over here where the lines are farther apart, the electric field is small. But everywhere on the map, the electric field is pointing in a direction perpendicular to the lines. And it points from high potential towards low potential. So if this is a potential mountain, then the electric field lines are pointing outwards. If this is a potential valley, then the electric field lines are pointing inwards. So this might be best understood with some examples. So let's start with the simplest possible example, and that is a constant electric field. So how do I show a constant electric field? Well, I have electric field vectors that are everywhere horizontal. They're all pointing in the same direction. And the electric field not only is everywhere pointing in the same direction, but it has the same magnitude everywhere. That's a constant electric field, shown by the yellow arrows. We can represent this electric field another way by showing its equipotentials. And the equipotentials are these blue dashed lines, all of which are vertical. They have to be vertical because the electric field is always perpendicular to the equipotential. So if I want my field to be always horizontal, my equipotentials had better be always vertical. And they're evenly spaced because the spacing between them tells me the strength of the field. And if I want the field to be the same everywhere, then I need the spacing to be the same everywhere. So same information shown in two ways. In yellow, I show you the field. In blue, I show you the equipotentials, and the fact that the equipotentials are everywhere vertical and everywhere spaced the same tells me that this is a way of representing a constant electric field. So here's a second example, also by now very familiar, one that we started 802 with. This is a single point charge. So you know from a point charge the electric field points radially outwards. That's shown by the yellow arrows. You also know that the field is stronger closer to the charge and it's weaker away from the charge. That's the 1 over r squared in Coulomb's law. That means that the equipotentials are circular, so that the field is everywhere pointing away from the charge, and the circles are close together in here and they're farther apart out here. That's the field getting weaker as I go farther away. So this is a way of representing the same information that we've shown as the electric field lines, representing it with contours or equipotentials. Third example, excuse me. Third example is an electric dipole. I've got a positive charge here, negative charge there. The electric field lines flow out of the positive into the negative. That's how we've represented a dipole before. But now I can ask, what are the equipotential contours? And they are these blue dashed lines. They're again perpendicular to the electric field everywhere. They're close together where the field is strong. They're farther apart where the field is weak. There's a special equipotential along the midline here. This is in fact the zero potential. It's halfway between the plus and the minus. And it's vertical because along this midline the electric field is horizontal. So this should give you an intuition for the properties of equipotentials. There are two principal properties that you should take away. First of all is that electric field lines are always perpendicular to equipotentials. And second of all, if you go along an equipotential, so if I go back to here, for example, if I go along an equipotential, I'm following along an equipotential, that is a direction along which there is no field. So there's no component of the field along the equipotential. So if I move a charge along this dashed line, I don't have to do any work. The electric field doesn't do any work. This is an equipotential. On the topographic map, this is a level trajectory, a level hiking path. So we now have three different ways of representing a dipole. We can look at the potential landscape. Here it is. We can look at the contour map of the potential landscape. Those are the equipotentials, the blue lines. Or we can look at the electric field. Those are the yellow lines. The same information shown in three different ways. So if somebody gives me the electric field, like here, how do I get the potential? Well, that's an integral, because the way you go from an electric field to the potential is by doing a line integral, as you've learned. Suppose instead somebody gives you the potential landscape. How do I get the electric field? Well, that's a derivative or a gradient or a slope. So the electric field, I get the electric field from the landscape by computing a gradient. What do those words mean? What they mean is that if I take a little positive charge and put it here, it's going to feel an electric force that is pushing it down slope. It's going to slide down the slope. That's the statement that the electric field is given by the gradient of the potential. So a little positive charge here slides down the slope. And always have to remember, unlike for topographic maps, because gravity is always attractive, but electric forces can be attractive or repulsive. So unlike for topographic maps, if I have a negative charge here on a potential landscape, negative charges slide up the potential landscape. So a negative charge placed here is going to slide this way. A positive charge placed here is going to slide that way. And the strength of the field that is pushing the charges around is given by the slope of the landscape. And hence, this diagram has all the same information that is in the electric field lines shown in yellow here.